Hey kids, Smath here. Gonna revisit electron configurations and teach you a few other things that we want to build on from that. Now, I just want to go back and visit what we did last week. What we did was we created this line of, hey, here's how we're going to fill orbitals from low energy to high energy. This is what came from our diagonal fill diagram, or our off-bow diagram is what it's called. And this shows us that when we place electrons in orbitals, we have to go from the lowest energy orbitals up towards the higher energy orbitals in that direction. And you have to fill an orbital before you can move on to the next one. That's just the way we're going to put electrons into orbitals. And we did this last week. We're going to do a little bit more right now. So suppose we have an element, something like sodium. I'm going to grab my blue and say, okay, what's the electron configuration of sodium? And so we just go, okay, no problem. We look at it and we find out sodium has 11 electrons. And then we go grab our line and we go, take the 1s orbital. That 1s orbital can hold, any s orbital can hold a maximum of 2 electrons. And then take your 2s orbital. It's an s orbital. It can only hold 2 electrons. Then go to your p orbital. This is a 2p. That can hold 6. Now, if I add up my superscripts, that's the number of electrons that I've placed in these orbitals. And so if I add up and I say 2 plus 2 plus 6, I've placed 10 electrons in these orbitals. I've got one more electron that I'm going to place, and that's got to go in the next orbital. So I grab my 3s orbital, and I can put 1 electron in that 3s orbital. And this gives me the electron configuration of sodium. We start low, we fill, move to the next, fill, move to the next, fill, move to the next. My 3s isn't filled. That's okay. It has a maximum of 2 electrons, okay? It can hold 2, but it can also hold 1. It can hold less than. Now let's look at potassium. This is going to be right below sodium on the periodic table. And potassium has got 19 electrons. Well, let's just start filling. I went 1s2, 2s2, 2p6. Now, I'm going to give you a little hint here. That 2p6 is always a real nice stop gap. Let's check that, because that's where I've already filled 10 electrons. Okay, 2p6, I've got 10 electrons in. I've got 9 more that we get to fill in. So what's my next orbital? A 3s. I can put 2 electrons in that. I've gone from 10 electrons. Now I'm up to 12. I've got 7 more that I get to fill. 3p6, 3p up here in my filling. That's the next one I get to fill. Okay, we'll go to 3p6. Great, but I've still got 1 electron left. At this point, I've only filled 18 of them. So now I've got to fill 1 more. And that 1 more electron I'm going to fill is going to be in the 4s, 1 electron. Now, I'm going to point this out a little bit later, but, you know, a little foreshadowing. Sodium and potassium are in the same column on the periodic table, and their electron configuration ends in the same ending, S1. These are both S1s, and they both are in the first column of the periodic table. That's not a coincidence. That's the way it's arranged. And so that's how we would do something like sodium and potassium. Moving over across the chart, we could do something a little bit heavier. Let's just keep adding more. Let's do gallium. Gallium's a really cool metal. It's got a very low melting point. As a matter of fact, its melting point is about the same as most people. It melts in your hand. So it's got a very low melting point. It's got 31 electrons in it too. So I'm going to grab 31 electrons, and we're going to go 1s2, 2s2, 2p6. That's 10 electrons. Remember, just told you that. All right, 10 electrons filled. Now we can go 3s2, 3p6. I'm at 18. Next one up, 4s2. Now if I go back to where I am on my diagram, I'm right here on my diagram. I filled the 4s. Next up is going to be 3d. And that 3d, all d electrons can hold 10 electrons. 10 electrons in a d. And so up to now, I've got 10, 18, 20, 30. I got one more electron to put in, and the next orbital I get is 4p1. Now this is a coincidence, and I just keep ending everything in one electron. It doesn't always end in one electron. Here, let's do one real quick that doesn't end in one electron, just so we don't go propagating that. Bromine has 35 electrons. Going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. We just keep filling up those electrons. Fill them up, move to the next orbital. Fill them up, move to the next orbital. By the way, I want to put just a little helpful note up here that for us to help, it'll say S can hold 2, P can hold 6, D can hold 10, and an F can hold 14. That's the maximum. All right, these are maximum electrons in an orbital. Doesn't have to fill. It can be less than filled as long as it's at the very end. Everything before the very end has to be filled up. These have to be filled. But the very last one does not have to be. The very last one does not have to be. But everything before it has to be filled up. So that's how we do electron configurations, again, just revisiting those. But what about ions? Ions are charged particles where we've either added or removed an electron. We talked about cations and anions, plus cat and anti-ion. So we're going to separate these and say electron configurations of cations, cation configurations. For cation configurations, these are positive. These are positive ions. And they've had electrons removed. So in this case, we've taken electrons off of these. So now, this happens very commonly. This is very common in metals. Metals are on the left side of the table. Left side of the periodic table. So now, let's take our sodium, same sodium we just had. But sodium forms a +1 ion. So that means that I had 11 electrons. Check it out up here. You can barely see it. I have 11 electrons up top, but this is a sodium plus. So I've removed one of those electrons. So now I've got 10 electrons. And that electron configuration is the one we said, hey, remember that one. 2p6. It's an easy way to count to 10. 1s2, 2s2, 2p6. That's 10 electrons. We like that. Very common. Let's look at another one. Let's look at magnesium. Whoops. Magnesium here goes 2+. And so magnesium on the periodic table, it's got 12 electrons. But magnesium ion, a magnesium cation, has +2. So we removed 2 of those electrons. That makes it 10 electrons. Oh my. 1s2, 2s2, 2p6. That has the same electron configuration. There's a term for that, and that's allowed. That's perfectly acceptable. These two species, they're called isoelectronic. And what that means, iso is a prefix that means the same. These have the same electron configuration. Are they the same thing? No, not at all, because sodium has 11 protons, magnesium has 12 protons. They're not exactly the same thing. They just have the same number of electrons. They're isoelectronic. Cations can do this, anions can do this, anything can do this, okay? So if we keep continuing through, we could do the same thing. It wouldn't be much of a surprise. We do aluminum 3+. Guess what? It was 13, lost 3, became 10 electrons. Same thing, 1s2, 2s2, 2p6. String that on down and finish that bracket out. All three of those things are isoelectronic. These are cations. Cations come from the left-hand side. So if we look at another cation, let's look at something like lithium. Lithium likes to form a plus ion. Normally lithium has 3 electrons. To make it a plus ion, it's going to have 2 electrons. 2 electrons. It's just going to go 1s2. Let's look at another cation. Let's look at potassium. Potassium forms a plus ion. Normally potassium has 19, but when we form the ion, it's going to remove an electron. It's going to have 18 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. There's a trend that's starting to happen now, and you can already see it. 2p6, 3p6. These ions tend to form a p6 orientation. Now these are cations. These are my positive ions. We've removed electrons from these. Now let's look at our anions, because they're going to do something that's real similar as well. They're just going to do it in a different way. So now we'll skip down to the next page and we're going to say, hey, what about our anions? Anions configuration. For these, we're going to add electrons. Okay, these are negative ions. And just like cations were common in metals on the left side of the periodic table, anions are going to be common in nonmetals. And those nonmetals are going to be on the right side of the periodic table. So common anions we're going to get. Let's start with something super simple. Let's grab oxygen. Oxygen's the most common thing in the world. It wants to form a -2 ion. Oxygen normally has 8. Now for these, we're going to want to add electrons to it. So this is going to end up with 10 electrons. 1s2, 2s2, 2p6. Now not everything has 10 electrons. Let's do something else. Let's look at a chloride ion. Something like, say, from sodium chloride. A chloride ion is Cl-. Now chlorine started with 17, but it's a -1, so we're going to add 1 to it, and we're going to make this 18. 1s2, 2s2, 2p6, 3s2, 3p6. Starting to see that same trend, aren't you? Ions end in a p6 orientation. And they do. That's a noble gas configuration. Are these two things isoelectronic? No, absolutely not. This one is in the 2p6, this one's in the 3p6. To be isoelectronic, they have to be identical. They must be. But we could do this all the way across. We could do this with a 3. We can grab a 3 minus, grab nitrogen. Nitrogen forms a 3 minus ion. Normally it has 7, but because we're making it an ion, it's going to have 10 electrons. Back to the 10. 1s2, 2s2, 2p6. Now, what we could say is, and I want to bring in all of our players here, we can say that Na plus, Mg2 plus, Al3 plus, O2 minus, and N3 minus are all isoelectronic because they all have the same number of valence, the same number of total electrons. So this is how we've revisited electron configurations. We've done anions, we've done cations, and in the next video here, I'm going to show you how to do noble gas configurations. So I'm Smath. These are electron configurations, and I hope that this video helped.